Okay, so we'll start with an introduction of our speaker. I think most of you, he needs no introduction. I think a lot of his students seem to be here, but I will still introduce him. We have with us Dr. Peter Todd. He is an experimental marine ecologist who focuses on urban marine systems. His team has 19 years of experience in the conceptualization, build, implementation and analysis of novel experiments, and over a decade designing and testing a wide range of sustainable shoreline solutions such as Biobos 2 at Changi Point, Rock Urchin at Sentosa, and Wedge Pool at Marina at Keppel Bay. So they are systems that are all around Singapore. So do head down to these places to have a look. You can ask him more about it later. And he's also currently the Associate Professor in the Department of Biological Sciences at NUS, where he runs the Experimental Marine Ecology Lab and is the Director for the Bachelors of Environmental Studies program. So we have with us Dr. Peter Todd. And 20% of Singapore is less than 5 meters above the Singapore height datum. I'll give you 3 options. You don't have to guess. A, 10%, B, 20%, and C, 30%. So A, 10%. Raise your hands. Wow. B, 20%? Okay. Okay, we have 2. And C, obviously everyone else is C, is it? Wow, 30%. Wow, so clever, everyone. Okay, you are right. This makes, so at 30%, this makes like the increase in sea levels rise an immediate threat to Singapore, right? Because we are a low-lying nation. Okay, question 2. To cater for long-term sea level rise, Singapore was raised from how many meters to how many meters in 2011 above the Singapore height datum? So to cater for long-term sea level rise, Singapore was raised from how many meters to how many meters in 2011? So is it 3 to 4 meters, A, meters, B, or 5 to 6 meters, C? So A, 3 to 4 meters. Raise your hands. 1, 2, okay, about like 3. B, 4 to 5 meters. Okay, now we have about 30%. And last one, 5 to 6 meters. Yeah, a couple, okay. So, well, it's 3 to 4 meters, so it's A. So this level, apparently, a study was done, 3 to 4 meters, is adequate in addressing the projected sea level rise under the second National Climate Change Study. So well, apparently that's the case. So 3 to 4 meters was the amount that was raised. Okay, last one. Our current efforts to defend our coastal areas from erosion include constructing walls and stone embankments covering up to how many % of Singapore's coastlines? Okay, our current efforts to defend our coastal areas from erosion include constructing walls and stone embankments covering up to how many % of Singapore's coastlines? So is it A, 10 to 20%, B, 40 to 50%, C, 70 to 80%? A, 10 to 20%. 1. B, 40 to 50%. Oh, 50% of the room. C, 70 to 80%. 2 people. All right, so surprise, surprise, it is C, 70 to 80% of Singapore's coastlines are made of walls and stone embankments. And the rest are all, besides this, the rest are apparently all natural areas such as beaches and mangroves. So actually a large proportion of Singapore is made of all these artificial structures. And actually all this, so I got all this information from the National Climate Change Secretariat under the Prime Minister's office. So you can go look there for more information. Okay, so now that we've learned a little bit more about our coastline, we can start off with questions. Maybe what I'll do is I can start by asking a question if anyone is too shy, but please feel free to jump in if you have a question. Don't feel shy, raise your hands and ask your questions, ask away. I'll start by asking, can you share with us about your journey into this field?
Yeah. Okay. like most things in life, not planned. So I there's a long version and a short version of this, right? So the medium version. Didn't like school. Left school as soon as I could. Trained as a carpenter. Worked as a builder. Got tired of the UK. Left the UK when I was 20. Went to Australia. Worked as a builder there. Stayed in Australia for a while. Left Australia. Went traveling around Southeast Asia. Ran out of money. Ended up in Taiwan teaching English. Spent 2.5 years there. Then travelled around again for another year. Then ended up in Hong Kong. Worked as a builder in Hong Kong, and then travelled around again for another year. So I eventually made my way back home to the UK when I was 27. So I have a past life. So from 17 to 27, I was doing something completely different. But sounds cliched. Sitting on a beach in India in 1994, I was like, okay, enough of this travelling, story. I'm going to go and learn something else, and go back to school. So went back to the UK, didn't know what I was going to do, and a friend of mine, an old school friend, suggested that I study ecology, do the same degree that he had done in pure ecology. And so I went to look up what ecology is. Actually, even after doing an entire degree on ecology, I didn't really understand what ecology was until more or less the final year. And I was like, I can't do that, I can't do a degree, I'm not that bright, and so on, I can't stay still for so long. And he was like, okay, just meet the course tutor, see what you think, right? So I had to borrow a shirt, borrow some pants, borrow a decent pair of shoes, and so on, and met up with the course tutor, Barry Giles, lovely guy, botanist, big beard like this, and graph paper shirt, classic academic, and he kindly took me on, gave me a chance, and that's important because I've, for better or for worse, I've carried on the same ethos with students who have less traditional backgrounds or maybe not so academically strong or whatever. I'm a soft touch. I will give them a chance. So that degree was ecological sciences, pure ecology, and I enjoyed it and did well, happily. And for my FYP, I'd learned diving in my traveling years. So for my final year project, my honors project, I actually co-led an expedition to the Caribbean, spent 3 months doing a diving expedition there. So that kind of tilted me towards marine stuff. Yeah. And then I worked for an NGO, a kind of cool NGO which had a ship called Ocean Defender. So we used to spend time on the ocean doing cetacean surveys, cetaceans, whales and dolphins. And it was kitted out for dealing with oil spills, interestingly. So that was fun. But I realized that the NGO life is not really for me. I'm from Manchester, so, like the center of the universe for cynicism. And that's not a good trait for being a conservationist and so on. It's like we struggle with, staying positive. And I also got a bit disillusioned with some of the inter-NGO politics and so on. So started looking for a PhD, and actually I wasn't leaning towards a marine PhD. I was open to anything. The three opportunities I got close to, one was doing deforestation in China, which I was interested in. Another one was meerkats in the Kalahari. Oh, wow. Yeah. Very cool. Yeah, very cute. Cooperative breeding. So I'd been happy with all of these. And then another one was this, because I was a member of the Royal Geographical Society, they had a magazine, and in the back of this magazine, they had an advert for scholarships to come to study at NUS anything to do with ecology or geography. It was from the geography department. So anything to do geography, ecology, physical geography, and human geography, the whole lot. And at the time I was applying for everything. The forestry one fell through because the supervisor got sick. The meerkat one, the meerkat one fell through because I got beaten by one other person, got to the interview stage. And then so I applied for this one in Singapore, and they were like, sure, I did a telephone interview back then, and they offered me the scholarship. So I came to Singapore in the end of 1998 to study to do a marine ecology PhD. And that was on coral reefs. So the degree I did was on coral reefs. It was interesting because I was in geography, but I was doing what we call phenotypic plasticity in coral reefs, which is how corals can alter their physiology and morphology depending on the environment that they're in, which is a fairly deep biological topic. So when I was in geography, people used to say, oh, why do we have this biologist here? You know, it's like, who's this guy? You know, what's he doing here? And then, of course, when I eventually ended up in biology, where I am now, they're like, why do we have a geographer? But for those, I'm sure you're all aware that ecology is essentially both of these are foot firmly in both camps. Biology and physical geography. Yeah. So then I did my PhD, did my postdoc in the UK on crabs, crab camouflage, and then was offered a job back here, which I started in 2005, and I've been here since.
Wow, what a journey.
So was that was a long, medium? I don't know, it was a much longer version, the average.
Well, if you want to know the much longer version.
Beer, yeah.
That's called Yard Below, and then that's where the beer is. Can. But yeah, I think that's really pretty amazing, considering I think people usually think like, oh, once you study ecology and then you get stuck in it and then you're just in it forever. But this kind of goes to show that you can really start from any point in your life. I think you started very much later into your life, like you said, 10 years later. Actually, I started very much later into my life as well. And while I was always interested in it, I didn't start till very much later as well. So start anytime. If you're interested, quit your job. And don't quit your job, but you know what to do. Okay, anyway, so I think one of the audience submitted a question and said, what's kept you doing this particular thing for so long? Because I think you've tried a few things and it's really, of course, very interesting, but there must be something that's keeping you going. Yeah,
well, I mean, I'm fortunate to, it's a great job. As a scientist, the main driver, which I think is true for all scientists, is the process of discovery. So, it's great to be in a position where you can work on topics and do the research and come up with something which nobody else has come up with before. And we even do that even at undergrad level. So my honours students, the projects that they have, it might not be a major leap forward, but it will still, when they finished it, they will have discovered something that nobody else has discovered. So the discovery is the main driver. But then the variety is another key element of being an academic, because you get to lecture, which is great, get to meet students all the way from first year undergrads all the way to your graduate students, your PhD students, and so on. So that's fantastic. You meet lots of great people. And then you do your research as well. So as mentioned, there's lots of aspects of the research which makes it intellectually stimulating and very interesting. And then there's the downside is that there's also a substantial admin aspect of it. There's a university is a big bureaucratic machine, so that can be very frustrating. But the good bits definitely outweigh the downsides.
Yeah, I do say like a job is like a big admin job usually. Like most jobs are, it's full of admin. But yeah, thanks. I think it's true. I think about scientific discovery, you're always discovering new things that people would have never seen it from this perspective, because you're just so focused at looking at this particular matter when you're researching or doing your thesis or your FYP.
And you get to go to, as an ecologist, you get to spend time in the field.
Yeah.
Ideally, not so much, because as in less and less, because you're running a team. But I was up at 4 o'clock on Tuesday, wasn't I, Carmen? Yes. In the field. So occasionally I will still go out.
Them yeah. I think that bit actually is what makes ecologists love their jobs, like really going out at odd hours of the day, because it's just so quiet and there are not too many humans, and that's why we're probably in this field, because we don't like too much interaction with too many people, right?
That's academics generally, leave us alone.
Yeah. Okay, now we will move on to a bit more technical and conservation questions, and I guess that's why a lot of you are here. We'd like to find out a little bit more about eco-engineering. I think maybe you could dissect for us what eco-engineering really means, and what are some of the main benefits of eco-engineered solutions, especially for coastal defenses. Yeah.
So eco-engineering, ecological engineering is basically trying to integrate natural systems with built systems for the benefit of both nature and humans. So that's the sort of the textbook definition. And how it applies to our coastal systems is in fact, actually, okay, so now's quite a good time to bring up a slide. Oh, okay. I forgot, this is my lab, or a slightly older version, but half of them are still here, but now it's changed a bit. It's usually about 20 people or so. Okay, let me. Can I go to just the whole?
Oh sure.
Okay,
yes, there we go.
Let me. Sorry, guys. I'm trying to. Okay, here we go. So prepared. Yeah. Have one ready. I've got 100 slides here, so I'm pretty much sure to have a slide for more or less everything, I hope. So nature-based solutions, which I'm sure you've all heard of, is a really large, overarching term that covers many things. So the things on the left you'll probably be very familiar with. So less engineering, so reservation, conservation, restoration, rehabilitation. So basically all the green stuff, all the soft stuff. Protect, obviously, as much as possible you want to protect what you have. And then as we move slightly more towards manipulating things, living shorelines, so now you're planting stuff, you're trying to get stuff to grow on the shore to contribute towards coastal protection. Then over here, we have more on the engineering side of things, so your green, blue, grey infrastructure, ecological engineering, eco-shorelines. All these are kind of homing in on this hybrid coastal defences, which I'll probably be talking about quite a bit. So on this harder side of things, certainly the work that my lab's been doing for the last 10 years or so is essentially, and this is actually not, there's quite a lot of cases where this is true for eco-engineering, where you're making the best of a bad job. So you already have hard infrastructure, or hard infrastructure is coming, like it or not. So what can you do to try and make some improvements, try and help, or try and do better than just a standard hard engineering approach. So I got into this because I was so one of the which rarely happens in other universities. One of the beauties of working in Singapore is that occasionally money pops up out of nowhere. In the university.
Oh, we all like that.
Yeah, we all like that. It's great. So there was a linking up with Delft in the Netherlands. So it's the Singapore-Delft Water Alliance. There's quite a lot of funding put in from both sides. We had lots of projects. And one of the projects which our Delft partners wanted to do was working on seawalls. What can we do with hard coastal defences to try and improve their ecological worth or value? And they asked, was anybody interested in doing this? And nobody put up their hands. So then I was like, okay, sounds okay, I'll try that. So that's where the initial funding came. And originally it was just like, okay, well, how hard can this be? You know, and we'll give it a go and see what happens. And then that was the start of what's kept, it's been an incredibly fascinating journey for the last 10 or 12 years. But basically that was dealing with what we have in Singapore. So I disagree about the 70 to 80% of being hardened. So our own research based on a map from 2011 had it at 63% hardened, right? 63% being hard. We think it's gone up a bit. There's been other studies that put it to 69, 70%. Wow. And then the soft bits aren't natural. Most of the soft shores in Singapore are also artificial. The beaches that we have on the East Coast, the beaches on West Coast, the Sentosa, these are artificial. So actually the soft habitats, most of the soft habitats are also artificial. So all the artificial habitats together make up, I think, 83%. Oh, wow. And then 17% is maybe natural. from our own research. Not that I would doubt, you know, the government office, whatever, you know.
I'll write to them after this.
You write, not me. So we got all this, and seawalls, just to clarify, because colleagues elsewhere, a seawall is like a vertical concrete wall. And we have some of those in Singapore. They're less common. What is more common, okay, just to press escape. Is this. Yeah. So this is what I assume you're familiar with. So this is what we call a granite riprap rivetment. Yeah, but we call it a seawall. But some people wouldn't call it a seawall. But when I'm talking about seawalls, I'm often talking about this. So these are granite blocks. Not a local, well, we have a granite quarries in Ubin, of course, but as a coastline, they're not really a local rock or local coastal rock. So not a rock that is really common in Singapore on the coastline, and it's a steep, much steeper than. Okay, I'm gonna.
Yep.
Okay, so here, natural shoreline, a soft natural shoreline. You put in a coastal defence. Often in Singapore, it's to retain reclaimed land, so that that expensive reclaimed land doesn't get eroded away. And then the issues with it is that it's steep, much steeper than the natural shore, so you have much less space for organisms to live, and the organisms that do live there get compressed so that they're kind of on top of each other. Different materials, so the granite I've mentioned already. Different hydrodynamics also related to the steepness, and then reduced structural complexity. And so when we went into this, okay, so what can we do with seawalls in Singapore? We can't really deal with the vertical steepness of different materials, altered hydrodynamics, because that basically requires removing the seawall and replacing it with something else, a new design. And we don't have a budget for that. That might happen in the future. You know, I mean, if a government decides that that's the way to go, that could happen, or it could certainly happen as seawalls come to the end of their life, and then you replace them with maybe an alternative. But realistically, that's not going to happen, certainly not at an experimental scale. My lab doesn't have the funds and capacity for doing that. But this structural complexity thing is something that we were able to do. We could add complexity to the existing wall. And that's what we have been doing in the form of these things, tiles, lots of tiles, tiles everywhere. Okay, this one, Biobos 2. So this is the culmination of quite a lot of research. So these are tiles that we attach. Do I have a picture? Oh, there you go. So these are at Changi, attached onto the seawall to create microhabitats which appeal to quite a wide range of intertidal organisms. So we can add this complexity, retrofit it onto existing shorelines.
Right. And how do you, maybe you could explain, like, how did you come up with this, and like what got you to this stage, to this particular design? Because I know you have like 3 designs, right? This, the rock urchin, and the wedge pool,
and some others. So, okay, so great question. Okay, let me zoom a bit. Okay, so it goes back quite a long way. Okay, I'm going to go back even further.
It's a complex process.
It's a complex, it really, okay, so increased habitat complexity. So the next question is, what is complexity, right? So we thought, like I say, we thought this would be easy. How many times do you think that? So we knew that we kind of, there had been some previous research done elsewhere in the world that had shown that creating microhabitats, drilling holes in walls and so on can create homes for marine organisms. So we knew that this was the way to go, or the general direction. And I had an honours student at the time, Lynette Lowe, and we drew some designs, some tiles. We knew that pretty much we were going to be retrofitting something onto the wall. So we drew all these fantastic, crazy designs, organic designs, and she was an artist, and they looked really cool. And we had maybe 5 or 6 of these designs. And we were like, yeah, they should work. But then we realized that if somebody asked us why, so say one design worked better than the other, and somebody asked us, well, why does that design work better than the other? We'd be able to say, well, we think it's because it's got this and it's got that. But we realized that we wouldn't really be able to explain it, which as a scientist is very unsatisfying. We like to understand things. Or certainly one of the elements that my lab does a lot of is trying to understand sort of the mechanistic processes, what's actually going on. So we basically chucked those out and went back to the drawing board. Lynette ended up doing her entire PhD on this. And so the first thing was to understand what complexity is. Okay, so then complexity in ecology is not well understood, but people realize it's definitely a thing. People know that habitat complexity is positively related to biodiversity. More complex habitat. This room is a good example. Yeah, smooth floor like this. You're not going to get lots of animals living here. There's nowhere to hide, and so on, right? Compared to outside in the tree, for example, lots more microhabitats, lots more life. So that's, that makes sense. And there's various ways of measuring complexity in the field. You can use fractal dimensions. You can lay a chain and see how long the chain is as it goes over all your bumps and stuff like this. But interestingly, we found that there's very few ways to create complexity. So various people measure complexity, but nobody really creates it, or not in a way that you can say this is more complex than that. And also there's something else that we wanted to deal with, which is surface area. So complex habitats tend to have more surface area and more, and there's not many laws in ecology, but there is a species area relationship, which really is a law. The more area that you have, the more species you have. So you've got more surface area, you're going to get more species. So we're interested to see, well, what happens if you control for surface area? Will complexity still have an effect? So I sometimes get my students to, okay, so our definition of complexity was basically, there's a complexity with a time component, which we were not interested in. Yeah, so ecological habitats are generally complex because they have time, they change with time. So ignore that, we just want a snapshot of complexity, right? And we call this informational complexity. And there's only a finite number of things that you can manipulate. And I sometimes get my students to do this. I'll give them a block of plasticine, and I'll say, okay, what features can you do with this block of plasticine to make it more complex? And there's only so many things you can do. You can stick things in, make holes in it. You can have things sticking out. You can make grooves. You can make some different shapes. You can make them lots and lots of them, fewer of them, different sizes, different X, Y, Z components. So, wider, vary your width and your length, but it's finite. And this is what we captured here. And then we decided to make some software. This is the first, so I love the design process, right? So this is the first, this is the back of the envelope, the back of the napkin one, so the first draft of the software, which then turned into this, which then turned into this, and then this. This is me. I was always teased because I'm an analog guy, so I like dials. Yeah, I want to be, but on my mixer like this. Yeah, but no, that got dumped into sliders, and then this was a beta version, and eventually we ended up with CASU, which is free to download. Yeah, so it's out there for the world to do. So this is to help you design your complex habitat, and then we apply that to this. So these are concrete tiles. And these top ones are what we call simple tiles. Everything is equally spaced, all the dimensions are the same. And then the bottom one, we stick it for our software, and it's essentially a randomization software. So then we randomize everything, but it's got the same surface area. So these got the top and bottom ones have all got the same they've all got the same surface area. But the bottom ones are complex, the top ones are simple. And this is the first big experiment that we did. And do I have... Let me see if I want to show. Oh, that's what it looks like. So this is the foyer of DBS, Biological Sciences. My head of department would be like, what's going on here? So all this metal work, all this concrete. This is an honours project. This was a Lynette's honours project. $35,000, the most expensive honours project we've ever done. Huge task, and not the last time that I regretted embarking upon something. It was a bit overly ambitious. But and just to, do I have the, I think, yes, look, this one. So this is us collecting the samples, the tiles in at the end, and then looking at everything that's on them. Lynette had to sort and identify 250,000 organisms.
Oh my gosh.
Yeah? Only. Yeah. Actually, no, you're right. It was 256,000. Yeah, there's missing out the 6,000 there.
Wow.
250,000 organisms. So we don't do this anymore. We now, on the spot, go over the tile and pick and see what's on the tile. We don't bring it back and clean it and examine everything. But it was great. It worked. We had this. Let's see. Do we have any results here? Anyway, yes. So the pits came out. The pits and grooves came out well, and I don't know. I don't have a plot here. But it worked. We showed very clearly that the complex tiles attracted more biodiversity than the simple ones.
Yeah.
And this. Sorry, I'm rambling here, but
no,
this,
it's okay.
this was also maybe also reflects another aspect of what the lab does, which I've tried to do all the way through this. So this study is 12 years old now. Is that at the same time, often applied research is I don't know, my colleagues aren't here. Applied research is not always most intellectually stimulating because it doesn't always have a deep theoretical component. It's an applied problem. We want to, conserve this habitat. We want to improve this. And so it's nice. What we try and do is have our pure ecology, our theoretical ecology, that research going on in parallel with the applied research. And this is a good example of this. So we were able to engage with a fundamental ecological question, but also come up with a solution that can help biodiversity on man-made shorelines as well. So that, and we try and keep on doing that. So we've carried on doing that for the last 10 years or so.
Wow.
So that's how, that was the first experiment. I'll try and be quicker with the other ones. We upscaled. Sorry, I realize these are not very good order. Okay, just in case you're curious. So the Casu software we use to create our design, and then you create a master. So a master tile. And this master tile is made out of wood. This is done in our workshop. We have a sneaky workshop at work. It's in a cupboard somewhere that I don't tell anybody where it is. So wooden master, covered in varnish to make it kind of waterproof, and then we use soft silicon to create the negative, and that's the mold, and then from that you cast the tiles. Right? So that's the process, and that's the process that we still use now. So after doing this experiment, we did an upscaling experiment, so we made bigger tiles to see if it still worked at larger scales. Again, you can see as hand making the masters and so on. This is also. Look, you can see here the cement mixer. So my lab used to be next door to a good colleague of mine who ran a molecular lab, so a genetics lab. So we were literally next door to him. So he's got a lab which you go in there and everything is pristine white. Oh. Yeah, and it's lab coats everywhere and PPE and it's
there you have this.
And then next door, literally, we've got cement mixer, we've got sawdust everywhere. He used to get so annoyed. Can't you do this somewhere else? No. So back then we used to make everything ourselves. Make the tiles, cast the tiles ourselves, do the whole thing. We don't do that anymore. Okay, so basically we did a run of experiments on different designs, different sizes. I'll come back to this one. Different materials. There was a lot of talk about pH. I don't know if you know, concrete has very high pH. It's about a pH of 13. So there's lots of talk less than 10 years ago, some time ago, about learn the pH of concrete and how this will improve the biodiversity. You get more biodiversity on them. We tested that. Doesn't work. pH has no effect. We tested. That's still a pH. This is us. That's me. In fact, drilling a hole. So we do quite awkwardly from a boat, because as you drill, as you push like this, the boat moves away from the wall like this. So
how do you do that?
We had guys on the top with ropes on the boat holding the rope to the wall. So cordless drills are your friend. 36-volt cordless drills, fantastic. Allows us to do this work in the field. This is at Lazarus. Then different materials. We thought that natural stone would be more appealing to colonization by marine organisms than concrete, because we've been using concrete, which is not a great material, right? The ordinary Portland cement, the cement component of concrete is really nasty, huge environmental footprint, big carbon footprint. So we wanted to see if stone worked better. We thought it would. No, not really. Not much difference with stone. Look, this is how overgrown they get. Yeah. So you can see the sort of growth we get after 6 months or so in the field, and you can see the rock behind it hardly has anything on it. So it's quite effective. It does work. So building the stone didn't really seem to have an effect. Green concrete. This is one of our most recent papers. So concrete, it's a useful building material. There's a reason why it's utilized. You're sitting on it right now, right? Easy to work with, easy to build things with, to cast. Strong, it's versatile, quite cheap, but has this big carbon footprint. Lots of talk about green concretes, and it's the wheels in Singapore turn quite slowly. BCA, is approving more and more green concretes, but it's a fairly slow process. I think at the moment there's green concretes approved for non-structural use in Singapore, so pavements and this kind of thing. And I'm sure in the future we'll see them being used for buildings as well. So green concretes are ones which basically reduce the amount of ordinary Portland cement. So you take the cement out of the concrete and replace it with other cementous materials which are not so harmful. So we tested a bunch of different green concretes to see if they have any positive or negative effects or neutral on marine organisms. So some of these were based on biochar, on marine clay, and some other, you also get ones made from furnace waste and incineration waste, this kind of thing. And the result was no different. So as you might have guessed from the previous studies, there wasn't any difference among the green concretes compared to regular concrete. And this is a good result. We weren't really expecting anything. We were worried that they might be negative, that would be bad. But the fact that they're all the same means that it's a viable option to switch out your regular concrete and use green concrete instead. Yeah, so that's an important finding for us.
But cost-wise?
A bit more expensive. But as with most things, as production increase, economics of scale, so the more people, more demand and so on. So now people are paying a bit of a premium, but it's not ridiculous, and the prices will come down.
Right.
So all these bits, all these things that we've learned to date were incorporated into BioBOS 2. The BioBOS 1 was this one up on the top left. So BioBOS 2 was meant to be a design that, or is a design that we can use at a large scale. Yeah, it's not. If I was in business, I'd call it a commercial design. I'm not in a business, but it's a design that we can use, actually implement. Implement at scale. Designed to, it weighs about 13 to 14 kg, so one person can lift it. We didn't want to have cranes and stuff like this. So one person can lift it. It's not. I mean, of course, a bigger one you can cover more area more quickly, but it's heavier. Smaller one, easier to work with, but you need lots more of them. So we thought it was a nice size, and then we went with the hexagon shape because it's you can tessellate it, so you can put them in clumps. It looks nice. We think so. And as you can see, it's got the pits and the grooves and the towers, which we were able to show in the earliest experiments that these ones work best. So that's what we've installed at Sentosa at Changi Point. We're now installing at Tekong, and I'm sure there'll be other sites in the future.
Is BioBOS 1 a lot smaller than, like, size-wise?
It is. BioBOS 1 is 20 cm by 20 cm by 20 cm, whereas this one is 44. Yeah?
Right. Very much.
So BioBOS 1 was for this graph paper one on the left. I will come back to that, but that was specifically for that job. But the urchin is directly related to BioBOS 1. BioBOS 1 was a really nice tile to work with because it was small, it was light, and I didn't mention that, but we attach these, that's what I meant to mention with the drilling. So once you drill a hole, you use a stainless steel bolt to attach the tile to the wall. So the BioBOS 1 was nice because you just used a single bolt. the BioBoss 2, you need 3 or 4 bolts, so it's more troublesome to install. And I missed the what's the word? The what do you call tactile? The handling of the BioBoss 1. It was a nice size to work with, right? So I wanted ergonomic, and there's a word that will come back to me. I'm sure one of you know what I'm talking about. So I wanted to make one which was smaller and was nice to handle. That would also, I was also asked to design one that would work on individual boulders, or that would work on different orientations. So I came up with so this one, just to be clear, this one is Lynette Loke's design. So she was, we worked together on lots of designs, but this one was hers. This was my PhD student, who's now a lecturer in University of Melbourne. But after she left, then I had to start designing my own tiles. And so the Urchin was one that I wanted to, small and easy to work with, single bolt. And it, if I say so myself, I like it. I like working with it, and it works well. It gets colonized very rapidly. It's great for citizen science. Anybody can do it. I get my students, my classes have a go at installing them and so on when we do field work. And it does go on anything. It really does. You can put it on any vertical, sloping surface, whatever. These ones only work on sloping surfaces. They're designed for sloping surfaces because they hold water that way, and holding water is also an important part of how this works. So that's how the Urchin came about. And then if I got these are, okay, so these are the ones at Sentosa, the southernmost point. Is that? More drilling. Go. Yeah. Hey, where was a sheep? Okay, that's the last one in. So there's always a celebration. Whenever we do an installation, the last tile in, it's always something to celebrate because it's a lot of work. Right. And you can see,
how many do you guys install at like one shot?
As many as we can.
Oh, right.
Oh, what, in one setting, in one go, in one day?
Yeah.
That's a good question. Depends on the size of the team. We get in. So this took 2 days. This was 2 low tides to get in about 80 units altogether. Right. So we do it pretty fast. Yeah. I think so. We've had lots of practice. And then these are the wedge pools. So then I was also asked to design, or we want to design a tile specifically for vertical surfaces. So they're called wedge pools because these are lots of little rock pools. So I should have started with this really. The intertidal environment is a harsh environment. It's full of marine organisms, but they're also exposed to the air, particularly brutal environment for marine organisms. And what they want to be, of course, as a marine organism, they want to be in the sea. So if you can have, and you all know about rock pools, well, actually rock pooling, we don't have many natural rock pools in Singapore, so it's not really a thing here. But a common thing in temperate countries, looking at rock pools, you get lots of things living there because when the tide goes down, the water is retained and things can stay there. So the same concept, you provide a puddle of water that the marine organisms can keep living in. So that's what we do here. And again, you can't quite see, but this is a simple version. They're all the same. And then next to it, we've got a complex version. So again, we're still testing this idea of complex versus simple, but in different situations. I said we had other designs. Yeah. So Life Circle was, PUB asked me to design one for Siglap Canal. Because quite a lot of the canals, the longgangs in Singapore, get flooded by sea waters at high tide. They're intertidal. Sometimes quite far in, 200 meters upstream. So we're interested to see if we could but they're very barren because they're smooth concrete. So they wanted to, can we make a tile specifically for the canal wall? And this one is too sticky outy and interfere with hydrodynamics, and you get garbage or whatever catching on it. So we smoothed it over, and this is called a Life Circle Falcon. For those of you, for any Star Wars fans out there. And we've made these, but we haven't installed them yet. because the Siglap Canal is still being built.
Ah, okay, right. So it's the newest project that you're on for this
That
particular
we probably
one.
won't see you for a few years yet.
Ah, right. So they are trying to improve the biodiversity within the canals. Is that what
They're
trying
interested
to
in it, yeah.
Okay.
Sure.
Okay.
I mean, it's an experiment, so try it out.
Yeah. What is? Well, before I ask anything, sorry. Yes.
And the longevity of these?
Good question. We're waiting for them to fall apart. We work with our engineering colleagues to make them as solid as possible. Some are more solid than others. This one is very solid. And they're made out of concrete. They should last, we hope that they last 20 years, but we see some erosion on some of them in the higher wave energy areas. Not that Singapore has really high wave energy, but it does have some parts where you get the ferries on. So the Sentosa one gets hit by the ferries. So you do get some erosion. If you get a wobble on them at all, then that wobble exaggerates. So we have to go and repair and fix them. But ultimately we want them to last for the repair life of the seawall. So the seawalls also get repaired every 20 years or so. So we'd like to match that. Yeah.
Any other questions so far? For me, it's like, what is the cost of like installing, I guess, one of these, or like the production of it and then the installation and the maintenance? What are we looking at?
Okay, so these are good questions and tough questions. So I have a master's student now who's working on this. So we're trying to, so you've heard of ecosystem services, right? So we've come up with our own term of eco-unit services. So basically, what are the ecosystem services you can get from a single tile? But a single tile is not really an ecosystem, so we call it eco-unit. So and then we want to try and balance that with the life cycle analysis of each tile. So a life cycle analysis is a cradle to grave approach. So basically, what's the environmental impact of the production and installation and disposal of a single tile? So that's there's calculations out there already for the cement component of it. We have to calculate some of the other components, the installation bit, the energy that you use, and so on. It's quite a complex process in itself. So calculate what is the cost of the tile, the environmental cost of the tile, and then try and compare that with the environmental benefit of the tile. So that's what we're doing now.
Right.
Difficult because different metrics.
Yeah.
So in ecosystem services, difficult to put dollar values onto them and so on.
Yeah.
So it's kind of apples and oranges, but she's having a good go at it.
Right. Interesting. Any other yes?
How are you continuing to raise money for it?
So the research is done through grants, so as most university research, and then the installations have been a bit of a mixture of, so the larger ones are funded by the stats boards, by the government agencies, and then the smaller ones we do it ourselves. We'll use the grant money to install in an experimental way, so we can collect data. So they tend to be the smaller installations, although some of them have been quite big. But the larger ones, it's really, and so there's some other people doing this in the UK and Australia, and the lesser extent in the US. There's some other groups working on similar solutions, and they might have private sponsors. They have lots of local government to go to and so on. Or local councils, that kind of thing. In Singapore, it's pretty much a one-stop shop. So the government either wants it or it doesn't, So if they want it, that's great, we can help. So actually our task is mostly about, one of our tasks is just engaging with the public, but also with the agencies to explain to them what we're doing and how this might be a benefit to Singapore. And they're getting more and more interested, particularly after the National Day speech by PM Lee in 2019, when he was mentioning, you were talking about Singapore's sea level rise and the existential challenge that it is to Singapore. So since then, there's been a huge surge of interest in defending Singapore and how to avoid building a wall around Singapore. which is kind of like.
Are we getting there?
I don't want to say, but that's the worst case scenario, right? So that would be the worst option, right? And then anything from that is an improvement.
Right. Yeah.
Why I asked is that I am one of the sponsors of Shorelines, which is a theatre group. And when you were talking about stones and putting all this stuff there, and I was thinking what Shorelines has been doing is selling seats, sponsoring seats. So I was thinking, why don't we get people, individuals to sponsor
a unit, right?
yeah,
Like,
and say, you can their name on it, whatever, and just say that's it. And I'm helping to preserve Singapore, helping to preserve life.
a coastline or something like that.
And
That is a great idea.
Because you could get schools involved, and that way, So I don't know why my brain goes from theatre seats to stone, but I just had that thought because it's the double thing of getting people involved, interested at a very low level. If you put years and years ago, it's the first time something like this on this line started was the National Library, and people like me, I was in primary school, and we helped to sell bricks. That has had, when they tore it down, that had this tremendous emotional thing. So I thought that's a good thing to have for this.
Right. Yeah.
Because this is, in a way, it's existential, and it is some part of our life.
Yeah.
I think it's a great idea.
Yeah.
And we hope, so we've got a new project starting up soon, and in that there's much more social engagement and education components of it. One of the ecosystem services is what we call cultural ecosystem services. So what amenity value, what educational value there is, and so on. So we're going to build up that, have more citizen science, and so that would fit in nicely with that whole idea. Yeah.
Because you were saying that Singapore is like one-stop shop. Yes and no. I know a fair amount about this because I was a journalist for about 30 years. And one of the interesting things that has happened recently in sports, you guys probably have heard of Max Mader, the kites.
Yeah.
Well, I was at a talk by Edwin Tong, the minister, and he said, well, he's very interesting because he just came out and said, we didn't have the money. Here's this rich country. We didn't have the money. We couldn't do it because just for one person. So somebody said, let's go look for a sponsor. And they went to Yo Hyap Singh and they just said, can you help us? We want to keep this boy here. He's half Swiss. If we don't do it, the Swiss will say, sure. We don't have him. He will be our guy in the Olympics. But he's doing it for Singapore. So I thought that this is something that has that kind of potential.
I'm sure you're right. I'm sure you're right. I think one of the issues for me personally is that I'm not very good at this. I'm an academic. I like to do my science. I'm always happy to talk to the public and stuff like this. But when it comes to fundraising and that side of things, it's not. I'm just not very good at it. Not my thing. So we are trying. And interestingly, it's not just me. It's my quite a lot. I'm always looking for people in my lab to do outreach and to engage and promote and so on. But they're also shy and don't want to do it.
Scientists being scientists.
Scientists being scientists. Scientists are going to science. But I am currently in discussion with some, and then of course then there's also the another route is a commercial route, right? So the commercialization of this, we get asked about that a lot as well. That's also complicated and also something I've got no interest in personally, but would be happy if a local company got involved. So it's a bit complicated. It's a bit upscaling to a large-scale implementation, is just it's complex and beyond my experience, to be honest.
But do you think it will take? Currently at this particular scale, do you think that it's viable to scale up very quickly? And how long do you think the scaling up would take? And is it so? For example, say if a company comes and go like, okay, I want to invest in this and scale it up like 1,000 times it is now.
Yeah.
Would that be very possible, and is it very quick to do so? I guess that would be the question.
I would say I would say yes to both of those things. These designs can be improved. They can always be improved, and if you leave us to it, we will just carry on working on it forever. At some point, you have to get on with it.
Yeah.
No, absolutely. These could be implemented at a large scale. Yeah.
Right. Yeah.
But if I may say, this is just one of a suite of solutions. So I just want to be very clear that these are meant as like I say, the best of the bad job. These are meant to be retrofitted onto a wall that exists that isn't likely to be torn down anytime soon. And maybe something that we can talk about a bit later, or move into is what are our new coastal defences going to look like? So, and to me, that's the bigger challenge, the bigger target, and where there's the opportunity to have impact at a global scale. As we see coastlines, every country is concerned about their coastlines. As we see more armouring of coastlines, it's increasing year on year. We've just finished digitising the coastline of all of Southeast Asia to calculate how much of it is hardened already, how much of it is seawall already. It's about 13%. There's a lot of coastline in Southeast Asia, and that number is just going to increase. So what I'm really interested in is as we alter these coastlines at massive scales, can we do a better job? Yeah, this to me is fun, but it's and interesting and good, and but it's a small solution. There's a bigger challenge ahead.
Right. Yeah. I think there's a question right there. Yes.
Yeah, I'm so sorry. Yes. I'm actually wondering because with climate change and all, sea levels are going to rise. Are these structures able to hold out? Will it be able? I mean, yes, we are getting the biodiversity back, but soon enough the water levels can get really high. Will it actually nullify the early efforts? How does it pan out?
Yeah, great question. So it'd be more the problem if this. Okay, don't get me wrong. But as far as your question goes, it'd be more the problem if the sea was going down, right? Because then the tiles are going to be left high and dry. As the sea goes up, the tiles get drowned, right? They cease to be intertidal tiles and they become subtidal. But they will still have a positive effect subtidally. You're still adding habitat complexity, but now it's subtidal complexity. And that's something else that my lab is also working on. We're working on artificial reefs and introducing complexity subtidally as well. So it won't have any, the tiles will still function, but in a slightly different way. And then you can just keep on adding tiles as the sea level rises. So as your intertidal zone moves up, you can add more tiles if you want to.
Where I'm coming from is because such structures, after all, they are meant to be intertidal in some sense. I mean, but when the sea level rises, pressure is different, water volume and all that. I don't really know how it can affect, it can change when the structures actually go out. Because if they don't go out, they can possibly just get washed away in the sea and become part of the
Right.
What do you mean? Sorry, what do you mean by hold out?
It's like the structures that are built there will
will get eroded away or like
will they
washed
stay?
away?
Will they be washed away?
Yes.
No, they won't. I hope not. So actually, the forces that you get, what we call wave action and if it's big waves, wave shock, those forces that you get are actually tend to be stronger in the intertidal zone because you've got your waves slamming against the wall. But if you're deeper down, then that surge is you don't tend to feel it so strongly. So
it's better under.
I think it's better under. I mean, as a diver, if you get caught in surge, you go down deeper and then you avoid it. I'm not worried about them being washed away, to be honest. But also there's timescale issues of this. I mean, it will take decades for these to become subtidal, and to be honest, they're probably in that time frame eroded or fallen off anyway. You know what I mean? So if I was designing them to last for 100 years or something, maybe it'd be a different issue. But I think in the big scheme of things, I'm not too worried about this. If they and also because they are concrete as opposed to plastic and so on, if they do fall off and they end up on the seafloor and so on, it's not the end of the world. You know, it's essentially rock.
Yeah. Yeah.
Thank you.
Yeah.
You shared earlier that like the pictures of the different 3D CAD designs of like biodiversity 2 and how they consist of many different types of shapes, like negatives and positives as well. I'm just curious about what kind of different organism recruitment you see of the different shapes because of their
I mean, basically, we get a lot of mollusks and crustaceans and worms and algae. If it's lower down, occasionally we get corals. It can be a bit disappointing to some of our people who are interested in, supporting this because they think they're going to have some garden effect, some beautiful biodiversity and so on. And it's mostly brown and slimy and creepy crawly type stuff. But we have found that you get quite good size matching with the pits and the grooves. So you get organisms tend to hide in the holes which match their body size, which is quite cool. And I had a student who just finished his honours project, and actually a year and a half ago. So he's into his PhD now, and he did a fantastic project on trying to understand why do they like those hidey holes? Again, you can guess. It could be, to avoid that wave action, to avoid desiccation and heat, to avoid predation. All these are possibilities, and they're probably all correct, but nobody had actually tested them. So he did a really nice job of partitioning these out, seeing he got lots of Nevite snails and made some tiles with holes, and then in the lab introduced them to wave action in a wave machine, and then he would toast them with like a electric ring like this to heat them up a little bit to see if they escape into the holes. All this kind of stuff. Really nice long string of experiments to see why they hide in the holes. Very good. Yeah. And predation as well. Yeah. So put them in, if there's predators around, do they hide in the holes? And actually, they hide in the holes for all of these reasons.
Not one or the other.
Not one. They all work. Yeah. But it was a nice study.
Right.
But basically it's inverted. Although as we go bigger, so this is us taking some of these concepts a bit bigger. So this is looking to see whether the complexity story also works with fish. This got so I have to say there's a lot of building work. I had a student bumped into the corridor a couple of years ago. I thought she was going to come to my lab. She was interested in marine biology. I thought she'd come to my lab to do a
It's a video.
Yeah. This is us getting the blocks down the seawall. So I thought she'd join my lab, and I was saying, I thought you'd join my lab, and she's saying, oh, I wanted to, but I can't. I'm a rubbish builder. I can't build anything to save my life. I was saying, you don't have to build stuff to join my lab. It's a biology lab, you know, it's an ecology lab like this. And she was saying, no, everybody knows that you've got to be a builder to join your lab. I was going, no. I was like saying, you know, when you leave a lab, you're a builder, you know, but you don't have to be one to start off with. You know, I've had lots of students who've never used a screwdriver join the lab. When they leave, you know, when they obviously fail to get a job as a marine biologist, they can get a job as interior designer, you know, as a construction worker. Yeah? But there is, the reality is that there is quite a lot of this heavy work, which doesn't, and also, funnily enough, when years ago when I was first doing this, you know, students would come along and say, oh, do you have any projects? And I was going, yeah, you know, I've got these seawall projects. And I say, no. And they say, you know, but you work on mangroves as well, right? And I say, oh, occasionally, you know, do you have any mangrove projects? No. And seagrass, you've done seagrass before? Yes. Any seagrass projects? No. Coral reefs? Yes, no. And so it's just seawalls. Yep, just seawalls. And we go, oh. And you know, they reluctantly do it, but then they get into it. Yeah. But more recently, and in fact, Carmen there, you know, one of my current PhD students, was one of the students to come into my lab and ask if there was a seawall project, which I was so happy. I was like, yes.
Finally one person.
Well, no, there's been a few, not many, but more as time goes on. Students are beginning to realise that this is a real problem, and that there's, you know, want to also. And naturally so, often our ecology students, they want to do something which they hope will have some practical benefits, something applied, something with some tangible benefit. So yeah, I've been getting more students over the years who actually want to do this, as opposed to me twisting their arm or trying to say, oh, it'll be great, it's fascinating.
Trick them into it.
Like this, you know, sailing by the mangrove. It's like, oh, no.
Looks so beautiful.
Sorry, changed our mind to the seawall.
We have a question.
Sorry.
Right there.
Okay. It's kind of following up on the question of what organisms occupy biomasses. So I was kind of interested when you mentioned that Kiwi was interested in using them to see if you can like create more complexity in reservoirs. But to my understanding, there are mostly like invasive species occupying reservoirs, and like there's not a lot of natives. Like natives are restricted to, say, streams or like just more naturalized like in the central area. So if you implement these, like does the complexity like kind of benefit in a way?
Okay, so there's a couple of interesting points here. So one is that we haven't used these in reservoirs, and we're not planning to. We're using on canals and on the intertidal part of a canal. So it's essentially still an intertidal system. So we haven't used these at all in a freshwater system. So Prof. down Yeo, who's the freshwater ecologist in NUS, and you know, my good buddy, neighbouring lab, you know, we've talked about this, and you know, we feel it's probably not. It might work, but there's no intertidal zone in the reservoir, so it'd have to be a below water in the reservoir. Now, so no immediate intentions to do anything on the reservoirs. The canals, yes, but the invasive story, yes. In other parts of the world, installing these tiles on the seawalls they've been colonized by invasive species, but we've not found that here. So whenever you create what we call a novel habitat, so a new habitat in an environment, there's always a risk that you might get some invasives opportunistically taking advantage of that. So we're aware of that issue. We've looked at it carefully. We get one species which may be invasive, but we find that elsewhere as well. I mean, it's basically everywhere, and so it's not special to the site. So it's an issue elsewhere, but not here, thankfully.
Hypothetically, if it was mostly colonized by invasives, would that diminish the eco-human service?
Arguably, yes. You know, generally we don't want invasive species, so it would be it's generally considered a negative thing. Yeah.
Yes.
With the recent oil spill, has it damages the things that you have installed.
Oh,
Yeah.
And they've been cleaning it, right?
Yeah.
And even if the oil spill did not damage it, the cleaning process
Yeah.
of the stones and all.
that's
It's
a
a
really
good
good one.
question. Yeah. So, yes,
Yeah.
there has been. So where the oil has been bad, if our tiles are there, then the tiles are affected too. Yeah. So this is so fortunately most of the sites where the tiles are weren't badly affected. Even the Sentosa site, we went and checked a few days after, it was okay. But at one site, I don't really want to say where, they were quite badly oiled. And then after being cleaned, they're basically back to square one. Yeah.
Okay.
And so that brought up some interesting questions about not just in relation to this, but also in relation to, as I was talking about, or mentioning future coastal designs, hybrid designs or nature-based solutions, soft options. How vulnerable are these to oil spills or any other type of these type of events? And is there anything that we can do about it? So that's been an interesting discussion in the lab over the last couple of weeks about can we future-proof new designs, new coastal designs against things like oil spills. And we think, there's some possibilities there. The main issue that is if you try and create for instance, a barrier, something that might keep the oil at bay, is that you reduce the connectivity of the system. But we're definitely thinking about it. But yes, I mean, basically, you can't avoid it. If your tiles happen to be caught in the oil, they're gonna suffer.
Right.
Yeah. It caused us some, and it wiped out a couple of experiments as well. So and to be honest, I felt more bad about that because of my students.
Oh,
So
had to redo the whole thing.
Well, it takes these are big experiments that every experiment that we do every field experiment is quite tedious. It takes months and months of planning and a building, and then the installation is a big job, and then you have to wait for things to colonize, and then you start collecting your data. So if everything gets wiped out by oil spill, City Yakub was also
City.
So when she was doing seagrass shading experiments at Passeris, and she sent me a WhatsApp, and a barge had swept over her entire site by accident, and just wiped out all her shading plots. All the frames were just flattened. It's hilarious. I've got I use it in my class all the time. It's like completely destroyed experiment.
So don't feel bad.
That's I told City, look, we'll put it to good use. Well, I will. But that's the nature of marine ecology. You get hit by a storm or any random events, can destroy your experiments. It happens.
I guess that's the beauty of experimental ecology as well, right? Because it basically in nature, everything you're like subjecting your entire experiment to nature. So anything can happen. An oil spill, a barge, something eating your experiment.
Something eating your experiments, this definitely happens.
Yeah, exactly. So
people coming and stealing your experiments also, or interfering with experiments,
Oh, that's not great.
We had we set up an experiment, Kusu, one of these, and we had a metal sign that we attached to
Do
the
not
seawall.
touch.
NUS do not touch, like this, and it's hilarious. Because they destroyed the sign, but everything else was left in place.
What?
So somebody stole the sign, but they left all the tiles untouched, which was quite, kind of cute. Making a point, I think.
Right.
Yeah. So we don't do it anymore. We don't bother putting the signs on.
Right. So I think we're almost at time, but are there any more questions on the floor before I wrap up? Because but I do have so many more questions actually myself.
I know, and I'm sorry.
It's okay.
My answers are very long, I realise.
Don't worry, but I think I do have one question also from the audience really, and it's really about how can community be involved and be encouraged in the planning of these eco-engineering projects. Like as divers, I think someone had that question, how can they be involved and in what way can they act? For example, could it be, for example, spreading awareness? Could it be raising funds? Like what do you think is effective for community to do?
Yeah, I mean, that's always a good question. I mean, so spreading awareness, raising funds are definitely there. The hands-on bit is a bit trickier because it's you know, a challenging environment to work in, and there's issues with that. I think probably the spreading awareness, but also this general making yourselves heard, making it clear to the decision makers that this is something that we want to see, or that you want to see, if you want to see it. So, for instance, at the moment, PUB has been having lots of engagement sessions to get feedback on some of their future plans. So, going to those sessions and sharing your opinion about how you'd like to see Singapore's coastline in the future is really important. The agencies really do listen. They are obviously interested in what their citizens feel about this. So yeah, having a voice is important.
Yeah, thanks. So I think really speaking up about issues that matter. For example, if you have, I think the Long Island project is the big one that's coming up, and I think they've been having quite a bit of engagement sessions as well. So I think it'll be great if you guys have strong feelings about it. Do make yourselves heard. Go for these engagement sessions. Find out a little bit more. And of course, if you would like to know more about Prof. Todd's projects, I'm sure he'll be happy to let you guys know. And he's got some of these brochures that he brought about the installation. So yes. Find out more from there. Do get a copy. I will just screen this now, but it's more like the ending thing. Yeah. So thank you so much for sharing with us. And of course, if you guys have more burning questions, I think you can stay for a little bit more to answer your questions. And next up for Wild Conversations, we'll be doing something a little bit different. The next one will still be at the end of the month. Last Thursday of the month, we'll be doing a screening at the projector. It's a screening on the Okavango. It is one of the greatest rivers on earth, and it flows through Angola into Botswana, eventually disappearing into the Kalahari after a 1,500 kilometers. It is a testimony to the interconnectedness of life on Earth, but also a chilling reminder of how quickly these pristine places can disappear. We will be joined by the representatives from Great Plains Foundation to hear more about what they do to preserve, rescue, and recover the African landscapes. So do join us. There are limited tickets, so do keep a lookout on our website and on our social media. If you like a ticket, it will still be the same. It will be free. And definitely don't forget to follow us on social media. I just want to talk a little bit more about this particular festival that we'll be hosting at the end of this year. It's called, okay, I'm not sure why this is not appearing, but it is called Singapore Nature Film Festival. It will be from the 1st to 3rd of November in Sentosa, actually by Emerald Pavilion. So do come. There will be a whole lot of nature films, and there will be panel discussions that you'll be interested in. There is also a call for submissions for nature and wildlife photography and also filmmaking. So if you're a filmmaker interested in photography and filmmaking, do hop onto our website to submit. Submissions close on the 8th of September. Prizes are fantastic, sponsored by Sony, and there's also a week-long dive trip to the Maldives by Ocean Geographic. So so do have a look at the website. We are at earthinfocus.co. So yeah, that's about it. So thank you so much for attending today's session, and stay wacky, wild, and curious. So we'll see you the next time. Thank you, guys. Okay, and yes, of course, if you like, we'll give this out to you guys.
Yes, come. Welcome.
Oh, wow. Sorry, I didn't realize. We'll hit the lights. There we go.
You like what? Thank you.
Thank you so much.
Welcome, welcome.
Oh,